That's a bit better. Hello everybody, how's everybody doing today? Hope everybody's doing okay today. I'm just drinking N juice. You can see it's labeled. Yeah, so how did the test go? Did you guys enjoy the test? Did you guys find the test to be, you know... I'm interested in soliciting generalized feedback about the test for the first few minutes of our lecture today. I believe we were on topic 7. Yes, quite. Ah! I should read some of the survey reviews. Okay. It was challenging. Challenging is okay. What's life without a little challenge? Ah! Mark is getting his vaccine today. I'm getting mine tomorrow. So... yay! Challenging but fair. Like that. Firm but fair. Not publicly. Okay. Fair enough. Yeah, send me a link, Mark, and I will take a look at that. Let's see. Our viewership is still increasing. I don't know, I guess I probably have, at this point in the semester, established a reputation for, you know, not doing any lecture material in the first 5 minutes. But, that might be affecting people's trickle in, but, you know. So it goes. So it goes. So. Alright. I guess everybody else is either not paying attention or just so furious that, they're not even capable of forming a sentence. Okay. Thank you. So, yeah. Well, we might as well get into our lecture material then. We were talking about testing. And we were talking about testing and exceptions. And I believe, you guys can correct me if I'm wrong, we were just about to get into finding the bug with the, this guy, max product. Presumably I'm correct. This course is going by fast. That's the thing. If this is your first summer course, yeah, we do not. This is a bus that's on a one-way trip to exam land, and there are no stops in between. We are not stopping for gas, and we are not stopping for bathroom breaks. Much as everybody would want. As much as everybody on the bus wants to stop at KFC for some delicious chicken and chicken-related products, this bus is not stopping at the KFC. Yeah. So, anyway. So, we were talking about this max product function. Just to review, because I know a lot has happened since Tuesday of last week. The max product function, the purpose of it, is to take a string containing numeric characters, that is to say, the digits, and to find the sequence of 12 digits within that string, which have the maximum product of any continuous set of 12 digits within that string. So, in terms of the algorithm that goes about finding this, it's reasonably simple. You just take subsequent... you could do this equivalently with a slicing operation, but you essentially take views of the data structure that move along that contain 12 characters. The construction of that view and the product from that view is represented with this inner for loop, which I can see the if statement is improperly tabbed, and this guy is improper as well. So, as that view moves along, we keep track of the products as they are calculated, and whichever is the maximum one that we calculate, we keep that, and then that's our return value. So there's a problem with this algorithm as written, though. So, let's take a moment and debug it. That's in my thesis directory. We don't want that. No, we don't want that. Yes. No, 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 no. Yeah, I kind of, I didn't bother trying to get an appointment, like, the first week for the vaccines, because I figured everybody's gonna want to get an appointment the first week, so, you know, patience is a virtue. So, get it. Topic 7.py. Burp. Nope. Oh, I guess this is not necessarily bad, actually. There. In Python, you can inline some things if you want, but I find it's, generally speaking, it's only confusing to people who are new to programming to inline things that aren't necessarily, you know, that don't need to be inlined. So, you know, yeah, anyway. I find using, like, you can use fancy stuff to get your code, like, compact and all that. Like, another one of these is list comprehensions, which, you know, I know Mark likes to use list comprehensions, but, you know, it's not explicitly covered, and it's kind of, like, extra syntax, and we're already, like, we're trying to teach, you know, this is fundamentally an introductory programming course, so, you know, we should be careful about how much crazy syntax we throw at you guys. Anyway, so the problem that we start running into is that we have a discrepancy between... so the reason that we know we have a bug is that with this particular example, there's a discrepancy between one of the test cases and the expected result and what we actually get from it. So let's take a look and see. Let's develop some test cases for this. So we'll want to, first of all, it's good to try one where the input is the minimal length, right? So we'll want 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Or if we include zeros, it'll always be 0. There we go. 12 digits, minimum input length. So if you can find out what the expected value is, of course, by examining your input and deriving some kind of theoretical conclusion. So obviously, if all of our numbers in this max product are contributing to the one final max product, right? Like, if there is only one subsequence that contains 12 digits, then you know that one has to be the max product, right? So you can just calculate out what's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 1 times 2 times 3. So this is our expected result. If we execute this code by opening up a new terminal tab, max product, or wait, no. Python 3 topic 7 .py. There we go. Oh, it doesn't bloody print anything. Happy Monday morning, everybody. We get 0. So 0 is not the correct answer. So we have already a mismatch between what we expect to get and what we actually get, right? So that's interesting. Some kid is playing with some remote control car on my driveway. It's interesting. Yeah. Anyway, so this is already a problem. So now that we've isolated the fact that we have a test case that fails, the next thing that we want to do is we want to reveal the internal data, that the internal goings-on, the internal happenings within our function itself. We can do this one of two ways. You can either use a tool such as Python tutor that will automatically display to you and reveal the information, all of the information about the intermediate states of the variables as you pull, your timeline across there, this timeline slide bar that you got. But sometimes this approach is not what you want to do, because the thing is, when you're debugging things, it's also extremely possible to have the computer divulge too much information. It's like the bug, you can think of it in terms of signal to noise ratio. Think of the sheer amount of information that's generated from having the program disclose its internal states. Think of that as being the noise, and only those particular sets of states that tell you what the problem is. You can think of that as the signal. So the easier it is, the less noise you have relative to the amount of signal, the easier it is to pick that signal out of the noise. And that's that's kind of a fancy way of saying, if there's just way too much on the screen, it becomes very difficult to actually decide, pick out what the bug is from all of the information that you're seeing. So sometimes you want to be a little more selective about the things that are being displayed to the screen. Generally speaking, the way that I go about doing this when I'm programming is I will start off by verifying basic details, and then I will proceed to verify more and more specific details as I continue the debugging process. So, something that's very, very basic is my algorithm being receiving its data correctly, right? Is my function receiving its data correctly? Is it being initialized the way that I'm expecting it to? So the way that you would check that is, of course, you would just print all of the things that are initialized. Product. You would just print everything that's either a parameter or a value that's initialized. This is, it's unlikely that you're going to find anything here, but sometimes it's a useful sanity check, right? So S is the string that we have asked for, and max product is initialized to 0. So this is fine. The next thing that you can do is you can go in to the next level, right? And you can print the states of I as it executes through this first for loop. Haha! Well, well, well. Well, well, well. Given that given that this has the I equals tag applied to it, we can see that that print statement is never actually executed. Well, isn't that interesting? This statement is never reached. We have not had to drill down very far in order to find what's probably the bug that we're looking for here, right? I would, under nominal operation, I would expect for this test case that this loop would execute, because if this loop does not execute, then it's not calculating anything, right? We've basically fallen over at the first hurdle. So this is never being executed, so I know there must be a problem with this loop. Probably somebody in the chat has already picked it out and has put it in. I just booked mine on the internet. Sorry, talking about the vaccine. I went to the provincial portal, and they got me. I checked Friday of last week, and they had one for me on Tuesday, this Tuesday in the afternoon. like tomorrow afternoon, so. I don't know. There weren't very many slots available, so they must have had a cancellation or something. But, you know. They had like a couple of slots. But anyway. So yeah. So this doesn't activate. So we know there's a problem with this for loop. So let's think about it. For I in range length of s minus 12. Well, one of the things that I like to do sometimes is, in order to check to make sure I'm looping over the correct thing, I find it useful sometimes to print the thing that I'm looping over, right? So print range of I is equal to, and then we'll just copy and paste this expression, and haha, range of I is equal to range from 0 to 0. Well, isn't that interesting? It's so the range of I is an empty list. It's an empty data structure. Well, so that would explain it right there. So now we know what the problem is mechanically, right? It's impossible for a for loop to iterate over it. Well, a for loop iterating over an empty data structure is the same as a while loop having its guard condition come out false initially, right? So, you know, if you have while false, the stuff that's inside of the while loop will never be executed, because the false value will, like, it basically turns off the whole loop. And the same thing happens with while loops if the data structure that you're iterating over is empty. So that's why this guy it's not doing anything. It's not executing. So we some of the more astute of you may have realized by now that the problem we have here is that the length of s, right here, is going to be 12. 12 minus 12 is 0, right? But the way that this algorithm is constructed, we the thing to keep in mind about range is that the range that's generated on range goes from the first element to 1 minus the last element. Because the first and the last element are both 0, we're generating an empty data structure. So, in order to generate a range that includes only the number 0, we actually have to add 1 here, right? We have to make the endpoint of the range 1 more than the number we actually want it to stop at. So, if we save that up, we now have range I is 0. So there we go. And of course, those of you who are algebraic simplifiers may notice that we can just replace that with -11, because that makes sense, right? And of course, that's just within the context of the print statement. We actually have to make the adjustment in the code itself as well. So, in theory, you could like take the variable out and isolate it. But so let's comment out our print statements and see if we get the thing we want now. Ta-da! Bum 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 bum. We now get the number that we wanted. But, well, anyway, we now get a number. Let's check to make sure that it's the number we wanted. 2177.260. 2177.260. Precisely! There we go. Wonderful. So we have found and neutralized the bug. Fantastic. Yes. So in general, that's my recommendation for a method of solving bugs, right? Start with the beginning and work your way to the end. Insert print statements that reveal, whether or not the things that you're expecting to happen are actually happening, right? Check your range objects to make sure that they're covering the range you want them to, It's like, you kind of just have to go bit by bit and, verify your various calculations. And sure, it's a little bit tedious to do it that way, but it works. Like, the problem with bugs, as I'm sure a lot of you have experienced this with your assignments and even possibly the midterm that you guys wrote on Saturday. When you have a bug in your code, you can't, sometimes you can just look at the code and see the bug, but most of the time, it's going to require you to pick apart the algorithm to be able to find it. And the problem is, if you don't have a systematic way of doing that, then you can pick it apart in such a way that you miss the bit that has the bug in it, right? So you can also think of decomposing your algorithm in terms of thinking about the statements in your algorithm as having their own input and output, right? In the same way that a function has an explicit input and an explicit output, statements, assignment statements, loops, any kind of programming construct, you can think of that as the state of the program before that statement as being the input, and the state of that program after that statement as being the output. And you can test things in that manner as well. So you require a certain degree of granularity in order to actually pick up on most bugs. So anyway, that's a method that I find works fairly well. It's not an understatement to say that if you're developing something that's real, you'll probably spend 2 to 3 hours debugging for every hour you spend developing, at least. And that's assuming things are going well. Anyway, so we have some other types of edge cases that would be good ones typical for max product. If we design the situation such that the product is minimal, i.e. 0, that would be cool. Design it so that the max product is maximal, so it's 12 nines all consecutively. And of course, you want to pick out the substring corresponding to the max product starting at the beginning of the string and starting at the end, and being at the end of the string. So So if you're thinking about this problem in terms of a window view into the data structure, you want that windowed view to be at the beginning of the data structure and at the very end of the data structure. Although it was this guy that picked up our bug for us, this one would also have picked up our bug for us. The max product being, erroneously at the... what essentially would have happened if we hadn't picked it up with this simpler test case is if we tried to do something longer, we would have eventually come to the conclusion that what it was giving us was a view that contained, that basically the view stopped one short of the end of the data structure, which of course would be that off by one error that we had fixed, right? So that's a problem that would have been revealed by this sort of where am I picking my answer from method of analysis. Good. So, once again, in order to verify what the result of your test case should be, you should use a method that's independent of the method that you're developing, right? So, using your good old Casio calculator. I don't know if they still sell this model in the bookstore at the university. I don't know if you guys have actually been physically to campus to see the university bookstore. It used to sell books. It now mostly sells sweaters. I guess sweaters make more money per unit floor space than books do. They do still sell some books, but oh man. I remember when we had the tank, which was a this weird cavernous space in the basement of like either Kenneth Taylor Hall or Togo Salmon Hall or one of those big buildings in the art squads, and it looked like a fish tank in there, which is why they called it the tank. And it was just like you had to go down these creaky metal stairs into this floor area that was like 2 stories tall underneath this 7-story building, and it was just filled with all your textbooks. But you know, the era of textbooks is kind of over in general, so you know, I'm sort of weeping for a lost world. Man, you guys have it easy with respect to textbooks. When I was going to school, you were talking probably like $150 a course. Unless you guys are still they've still managed to charge you that much for your books, even though you guys aren't really getting physical books most of the time. Anyway, testing. So, one way that you could have picked out that it's giving you one less than the one you want is by playing with it so that the correct result would be that one and that end window, and the correct result would not be that end window. So, you know, in theory, under ideal circumstances, if you add a 1 here, that shouldn't affect what the value of the max product is, right? The max product is going to be, you know, this selection from 6 to 9. That's the maximal product. If you add 1 to the end there, that shouldn't affect the value. But of course, if you still have that off by 1 error, then you're not getting the correct window, which means that test case would also fail. So anyway, as we've already established, the bug is that this 12 should be an 11. And that's, you know, so it goes. We have found the bug. Let me see if we have any questions. Yes, no. What's our viewership like right now? Ha! Even fewer people. That's not surprising. We always have a bit of a attendance drop-off after a midterm. So, so all of that we were discussing, all of that is black box technique, right? Because we're focused primarily on test cases and do test cases come out correctly or not. Now, it's a little bit disingenuous when I say that, because while the method of analysis that we used to determine the existence of the bug and to, you know, sort of suss out some of the features of the bug, while that was black box related, in order to actually fix the bug, obviously we need to at some point modify the underlying source code. And because we need to modify the underlying source code, we need at some point to have access to it. We need to see it. We need to use Whitebox Techniques. So black box techniques are really good because, you know, they're built for modularization and abstraction, but sooner or later you're going to have to modify the source code directly. And, you know, at that point, you know, you have to rely on your knowledge of the source code in order to fix the source code, to fix the black box test cases. So, let's talk about some white box techniques. So, code review. Sometimes you can have a code review where 2 or more developers will visually inspect a program. They tend to look for things like programming best practices, potential inefficiencies, or common vulnerabilities. When we get into SQL programming, we're going to, or databasing, we have a unit on databasing coming up where we're going to learn a little bit of SQL, and in that unit, we're going to see injection attacks. And injection attacks are actually a fairly easy thing to pick up on if somebody else is just kind of proofreading your code. It's like, oh, well, obviously you shouldn't do that because you're introducing a vulnerability with respect to injection attacks. The only thing is that this, like, code review as a process is a little bit expensive because you have to pay people to do it. And people's time is valuable. And the most expensive component of any system involving human beings is the human being. So there you go. So yeah, the other thing is you do have, like, standards of programming practice, right? And this is kind of getting more into engineering territory as opposed to computer science territory. I know I have hardly any of either of those groups in this class, but it might give you an interesting window into the world of engineering if you ever cared, if you care to have such a window. So, in general, so if you were to draw an analogy with something like structural engineering has, it has codes, right? There are particular manners in which you combine certain components to make buildings or windows or bathrooms or whatever. That's not structural, but you get the point. Well, plumbing. There are standard practices with respect to the manner in which you install a toilet in a building, right? There are, these standards of practice have come about from many, many, many years of people installing toilets in buildings. Part of the problem that you get with software engineering is that software engineering is a very young discipline, relatively speaking. People have been working as civil engineers for, I think probably around, I think it probably dates back to the early days of the Industrial Revolution. And before that, you had the Masons, of course, who had, as much as people, think of Freemasonry as this kind of, interesting little boys' club that, you join primarily if you're Scottish, the sort of Guild of Masonry had its own standards of practice, and that goes, those standards of practice were established during the medieval period, right? So, the manner in which you place blocks on other blocks to make a castle, that's something that is specialized knowledge that a mason would know how to do, right? So, because software is so young, a lot of the sort of standards of practice have not yet been established. The other thing, it's kind of interesting, in software you don't necessarily apprentice. If you're going to become a mason, you would take an apprenticeship with someone who is a mason, right? Same if you were to do, any number of sort of that sort of work. With software engineering, software engineers are largely expected to be self-taught. While having a degree in software engineering or something like that gets you a certain distance down the path, most of the people who are, shall we say, the sought-after commodities in the field of software engineering as a marketplace, as an employment marketplace, the sort of top end of software engineers are going to be typically self-taught. And because you're self-taught, not, you didn't apprentice into this position, you're not exactly carrying forward as much of a, sort of, like, you don't have that sense of tradition in software engineering. That being said, with some of the older languages, like C, there have been attempts to introduce the idea of standardization. There are some constructs that you use in certain ways. There are other constructs that you don't. Like, in C, we have the possibility of using a thing called a goto statement, which is basically it allows you to perform an arbitrary jump to any position in the source code from any other position in the source code. And in general, it is considered verboten to it is forbidden to use goto statements, despite the fact that the language supports them, because generally speaking, over the course of many years, we as a species came to the decision that goto statements are never useful because anything you can do with a goto statement you can do with functions and if statements and while loops. The sort of standard method of going about programming doesn't lead to states called spaghetti code. Spaghetti code is a state where your program looks like a big ball of spaghetti because you have different execution strands interweaving with each other and just looping in and out, and you don't know where one ends and the other begins, and it's just a big mess. So, programs can be enough of a big mess without having to worry about spaghetti code. So, that said, when I do a C class, I still teach goto statements because I take the position that you guys should still learn the forbidden magic, even if you're not allowed to use it. Knowledge of the dark arts is the best defense against the dark arts. But it's kind of neither here nor there because this is Python we're talking about in this class. But anyway, so there are standards of practice in programming, and you can be evaluated as to whether or not you're complying with them, but generally speaking, only by somebody who knows the standards of practice quite well, which means usually like a senior guy at whatever organization you're working at. Anyway, there are also tools, like you can have automatic tools that can assist in this review process. Some of the standards can be picked out automatically using syntax analysis, and there are tools that do that. There are also formal code review methodologies, although I imagine these would vary by the company that you're working for. So IBM probably has their own methodologies, and Apple probably has their own methodologies. All of these are very time-consuming. So time-consuming generally in software means you don't do it unless there are negative consequences to not doing it, right? If not having bugs in your program is critical, then basically the amount of time and money your company should spend on these types of testing, this type of testing, should be proportional to the criticality of that software not having any bugs in it. So, to some degree, like, if you're talking about a video game having bugs in it is bad, because people will not buy your game if it has too many bugs, or people will stop playing your game if it has too many bugs, or people will make hilarious cringe compilations on YouTube if your game has too many bugs, which might actually wrap around and be an actual benefit, but generally speaking, only the hilarious bugs count in that respect, and most bugs aren't hilarious. They're just annoying. But if you're making, for example, the software that goes inside of an MMRI scanner, right? Or is it MMRI? No, it's just MRI. The software that goes inside of a medical device, like an insulin pump or something like that, right? If the software inside of an insulin pump screws up, you could put someone into a coma and they could die, right? Which means that the consequences for failure of that software are much, much higher than, any degree of commercial lack of commercial success that you might have on the new Assassin's Creed game or whatever. Although I think Assassin's Creed does just fine no matter how many bugs it has in it. So, yeah, so we have a class of applications we call safety critical systems. Things like medical devices or nuclear plants or, air traffic controller software, or, the software they put in planes even. Stuff where if the software screws up, human lives are at stake, These are generally the sorts of applications where it's not even that the company will necessarily decide to do all of these time-intensive code review processes itself, but there will be regulatory requirements that come down from the government on the degree to which these systems are verified. So you can imagine it being perfectly reasonable for the government to regulate the correctness of the software that's put inside of a nuclear reactor. If you want to hear more about that, you should talk to Dr. Wassing or Dr. Lawford. So, with respect to... Okay, so we've talked about Whitebox a little bit, but how does it actually work? One of the practical ways that you can use Whitebox testing to verify your code, like not some external review process, is you can check for code coverage. So, all code coverage means, really, is that every statement in your function has a test case that exercises it, right? Like if I write a simple program, something like, if n is less than 10, elif n is greater than 20, else, do some third thing. Let's imagine this guy's just sort of sitting there in the middle of our code, right? We would want a test case that tests this branch, and this branch, right? You would want to test n being, something less than 10, like 3, something greater than 20, like 40, and something between 10 and 20. Because if there's a bug in this branch, in the else branch, and you don't actually test it, then that bug's not actually going to be found before you ship your software, or you send it to us to be auto-graded. And, while I will not assert that the auto-grader is perfect at picking up bugs in your code, it does a pretty good job most of the time. So, yeah. Pardon me. So, in order to make sure that your test cases actually exercise all three of these conditions, you have to know that these conditions exist. And in order to know that they exist, you have to use Whitebox analysis. That is, you have to look inside the box. Additionally, there are static analysis tools. We can run some automated tools to find common problems in programs. This is less relevant for things like Python than other languages like C. So in C, you have to do specific things in specific orders in order to manage your memory correctly, for instance. So in order to use a list, in order to use an array in C, like a list in Python, you have to build in dynamic allocation, which basically means it gives either more or less memory depending on what you're trying to put in or take out of it, right? But you have to do that manually in C because C is a very low-level language and it doesn't, C doesn't do a lot for you. And that's one of the things it doesn't do. So whether or not your memory is, for example, being deallocated when you're finished with it, that's something that you can check for automatically using a static analysis engine in C, but many of these types of issues are done for you in Python, so you just generally don't have to worry about them. The question then becomes, so why would I ever use C then? And the answer is because if you want to do something that's like outside the box thinking, you can use C and possibly gain extreme amounts of like efficiency. But anyway, so talking about well, it's actually 10:19, so why don't we leave the debugging section for our after the break, and we can go get biscuit or whatever it is that you want during the break. I'm probably going to have a biscuit. Anyway, see you in a few minutes, folks. And we're back. Hopefully. Just gonna test my sound because I've been caught on that one too many times. My goodness. Good. Alright. So, let's talk debugging. I've kind of already gone through this, but we'll go through it once again. So, debugging. Once your testing has shown that your program does not behave as intended, you have to identify the bug and then fix it. To find the bug, you need A, a test case that reliably fails, and B, you need to understand the internal state of the algorithm. You need to know what the variables are doing. To understand the internal state of the algorithm, you've got two options primarily. You can use print statements to print out potentially relevant variables. This is like, I consider that to be the bread and butter of the programmer. Like that's, if the plumber's go-to weapon is the adjustable spanner, then the programmer's go-to weapon is print statements, not go-to statements. An alternative, slightly more fancy approach is to use a debugger to step through the program. So debuggers are a little bit different in how they operate than Python Tutor. I'll point out the differences. Tutor, there we go. So if we just load up, close that. If I just load up this algorithm that we were working on, there we go. So, ordinarily, the way that a debugger works is slightly different from the way the Python Tutor works. In Python Tutor, they give you this timeline that you can zoom through to see the internal states of the programs. In a debugger, more traditionally constructed, you would set a breakpoint. You would click on a line, it would highlight it in red, or it would put a little stop sign by it. And what that meant, what a breakpoint is it tells the program to execute until it hits that statement. At that point, it pauses. Because it's paused, you can, examine the variables. You can, you can step through the execution from that point. You can go one line at a time. That can be useful as well. Some of the fancier ones. I think I've seen ones that you can step backwards as well, which is kind of cool. But essentially, the idea of a breakpoint is, again, like Python Tutor is good, but it's built for small things, right? If you have a sufficiently large program, you will probably want it to just run through its paces until it hits a certain point, and that's the point at which you're having the problem, right? So, so that's what a breakpoint does for you. It allows you to just run through at regular speed until it hits a certain point, and then you can step through. Python Tutor is, of course, limited to the amount, to the size of things that it can handle, right? But breakpoints can be applied to any program in general. So you just have to use a good debugger. So there we go. So one of the so idle is an integrated development environment for Python. It's built into Python installations. I can run it by typing idle 3, I believe. Load it up. Maybe. Idle. Maybe I don't have it. Not found. Well, at any rate. Maybe it's here. Idle. No. Okay. Well, at any rate. In idle, you've got 3 things going on. You've got the pane in which you have the actual program. You've got a Python interpreter, which allows you to, test particular. It allows you to test code. Run this function, run that function, in the same way that I use the Python interpreter while I'm teaching class, but I generally don't link it up to a file. This will link it up to the file you're working on, which is cool. Simulates more like the Jupyter system. And then you also have a debug controller. So you have the ability to set breakpoints, step through code, view the locals and the globals that are instantiated in this at that line. You can see what the values are. That's extremely useful. It's extremely useful. However, debugging is kind of a use whatever works for you kind of thing. I'm not going to require you to use any particular debugger in this class or anything like that. This is primarily FYI. It's primarily so that you understand the tools that are available to you. I hope that I have, while teaching this class, given you that information before this point. We've been using Python Tutor, I think, since the first lecture. It's an extremely useful tool because of the manner in which it visualizes stuff correctly with respect to stack frames and stuff. I really like that about it. So if you're already debugging using Python Tutor, good for you. There's no shame in using the tools available to you, right? A carpenter is not ashamed that he has to use a hammer to drive a nail instead of the flat of his palm, right? Although, I guess if you were a carpenter and you could drive nails with just the flat of your palm, that would be pretty badass. But it's not a requirement. There's no shame in using tools. Anything that you can do, like at this point, you probably have already developed a certain number of tricks to find bugs and try to fix them. And anything that we sort of layer on top of that, if it's useful to you, keep it and use it. Keep it and use it insofar as you find it useful. If you don't find it useful, don't use it. Use something else. Try something else. Just give it a chance before you just throw it out the window. Because these things are useful. You generally just have to figure out how to integrate them into your workflow. So anyway, so let's talk about exceptions. So, exceptions. What is an exception in general? In general, an exception is any of these errors that you've been getting. You know, we've been getting lots and lots of errors throughout our experience of programming with Python. So, for example, if I'm trying to interpret as a float something that is clearly not a float, potato, I get a value error. Value errors are a type of exception. So we're going to talk about how to deal with these exceptions. Up to this point, when you have gotten an exception, it's just crashed your program, and it's like, oh, back to the drawing board, nothing I can do about that. But it turns out that exceptions actually do have a practical purpose for the programmer, other than to tell them they're wrong. So let's consider a problem, right? Suppose we wanted to create a function that returns the maximum number in a list. This is basically the problem, what do you make the default value into, right? If we have this function that calculates the maximum of a maximum element in a list, and we are given an empty list, what should the correct response be? Let me see. Have I just lost the chat? Have I lost the plot? Nope. Okay. So, should we return 0? Probably not. Because, you know, it's not obvious. Like, while 0 is often a default value that you would go to for, you know, this, that, or the other. In this particular case, what if, you know, you're primarily dealing with negative numbers, right? 0 isn't even like the most, it isn't even the most negative number, right? It's not the minimal possible result. It's in the middle, actually, if you consider the negative numbers. So 0 doesn't really make a lot of sense. It wasn't actually in the list, so we shouldn't return it. Should we return infinity? Should we return negative infinity? Should we return not a number? That's about some programming languages, like JavaScript, I believe, have a not a number designation that they can assign to variables. False. So this is getting closer, right? So the way that we've been handling this problem so far in the class is whenever we hit an issue, we return false, right? If the input is outside of the range of the acceptable inputs, that's another way of thinking about it, we return false. Basically, what we're talking about is a domain error. So if you think about a mathematical function, mathematical functions are defined over a certain domain. If you consider like logarithms are not defined for negative numbers, so the domain is the positive, it's like greater than 0 is the domain of the logarithm function. So the problem with returning false is that we would need to check for false each time, right? So that would mean that each call to our function would require each call to our function to be embedded within an if statement within whatever code was calling it. This is, generally speaking, bad software design. We are going for modularity here. Modularity means that the only thing that we have to worry about when we call a function is the calling of the function. We don't have to add, we don't have to embed it in this, this arcane complex of additional conditions, right? So long as the input is valid, the output should be valid, although it's a good idea to check to see if your input is valid before you give it to a function. You don't want a function call to have strings attached. And if you make it false, if you make the return value for a domain error false, there are strings attached. You have to check the output to see if it's false. So this also would become problematic, assuming this, this function is used by other functions, which it's likely to be. If we have a bounding function, which finds the difference between a max and a minimum, if this guy might return false, what is false minus 6? Right? I mean, in this particular case, it wouldn't happen because it's the same list being used both times. So false minus 6 is minus 6. How does that even make sense? False minus false is 0. What, I'm getting integers here. Doesn't make any sense, right? So our solution, well, in order to make that actually work, you have to include all of these if statements, which is just a pain in the keister. So, we're not quite. So we're going to use exceptions to solve this problem. Here's another motivating example for why we need exceptions to solve our problems for us. What should happen if you pass a string to an integer conversion? Should it give 0? That's not actually what's entered. Should it give false? False isn't an integer. And if you're wondering why this goes on, by the way, it's because the underlying integer representation of false is 0, right? If you interpret 0 as Boolean, you get false. If you interpret anything other than 0 as a Boolean, you get true, including negative numbers. Yes. So basically, if you look at the things at the bit level, all zeros is false. If there's a 1 anywhere inside of that block of memory we are calling a Boolean, then that's a true value. Yes. So, you thought that Boolean values occupied only 1 bit in memory? My goodness, that's not true because of addressing problems and stuff. Anyway, so false, we're trying to get away from using false as a return value. So, as I demonstrated, the integer interpretation of a potato is a value error. So, exceptions. Value errors are a type of exception. Exceptions allow Python to deal with situations where it tries to execute a statement that isn't well defined or violates some condition. Python raises an exception. Raises is the verb that applies to the creation of an exception. This interrupts the normal flow of execution. We can have handled and unhandled exceptions. All exceptions thus far in the course have been unhandled exception. A bee is trying to get in through my window, but it's made of glass. Ha ha! I'm so happy. Sorry. I've got a window right here. It's fun. So anyway, in order to handle an exception, we're going to use try except blocks to, and we're going to see how those work. But they don't work very dissimilarly from if statements. They're like, if you understand if statements, it's not too far of a stretch to get try except blocks. So, yes. So, when we try to integer convert potato, we get value error. Invalid literal for int with base 10 potato. There you go. But what if we had base 32? That is actually a number, because this works in the same way as hexadecimal. But, yeah. So potato is not a base 10 number. Potato might be a base 32 number, but it's not a base 10 number. So, let's write a simple program. try. Enter input. Oh my goodness. I hate it when it does that. I'm balancing it on a book. The tripod wasn't quite large enough. Suppose I should get like a rod that extends from the base of the tripod to the camera. Anyway, so input. Enter number. Fool. Accept. Input. I pity the fool who didn't enter a number. And so you can say x is equal to, you can say x is equal to that, print you entered the number x. Fool. These are references to the A-team. So, if I execute this code, Python 3 topic 7.py. There we go. Enter a number, fool. No. What? Oh, that's input. Print. I wanted to print that. No. Oh. Right, because it has to be integer converted. Wah, wah, wah. Right, because the thing that might generate, the thing that'll generate the exception is this call to integer, right? I didn't have that in, so I wasn't actually triggering the try except block. Enter a number, fool. No. I pity the fool who didn't enter a number. Try it again. Enter a number, fool. 7. You entered the number 7, fool. So, let me explain how this works. When you put something inside of a try block, what you are telling the computer is, if there is an exception which occurs during the execution of this block, stop executing the block and immediately jump to the except clause, right? So, so we're going through this try block. We're, having a good old time. We get our input. We try to integer convert it. Uh-oh! That causes a value error. The value error says to the try block, stop! Hammer time. Just kidding. I don't know why it's so 80s in here right now. So we stop here during the execution of this integer conversion statement, and we then jump here and execute whatever is in the except block. What that means is, I believe x will never actually be assigned to. If we, so if we enter a number that's not a number, yeah, we get name error, x is not defined. Whereas, if we do enter a number, we can print x because x exists, right? This assignment statement comes after the integer conversion in the order of operations that this, the way that Python breaks this expression into a series of things to be executed, this integer conversion comes before the assignment statement. Because this integer conversion raises an error, x is never assigned to, which means that it is an undefined variable by the time we get, after everything. So yeah, it's actually not too bad. try except blocks. The trickiest thing to understand about try except is that that Python will stop execution dead at the first exception that it hits and then jump to the except clause without having completed it. Without having completed the rest of the try block. So from a design perspective, the thing that you want to make sure with these try except blocks is that whatever is going on after the try except block, you want to make sure that your program is not going to be left in an unstable state, right? So another way of saying that is you don't want to introduce more errors by not doing everything that you need to do inside of this try except block. So because X is being initialized inside of a try block, incidentally, you should probably initialize X outside of the try block, right? If you just moved this here and did that, then everything would be fine, right? Introducing X before you get to the try block means that it's absolutely going to be a registered variable before, regardless of what goes on with this. The alternative to that would be to put it inside of the except block. That way, even if we get interrupted before this variable is created, it's still going to be created in the except block, so by the time we get to the print statement, it's still going to be there. But again, initializing your variables up front is usually the preferred path for these sorts of things. So there you go. Cool. Let me see if there are any questions. No questions. Anybody paying attention at all? Hopefully at least 3 people are paying attention. It's okay. It's a Monday. I get it. So. Handling exceptions. You put code that might cause problems inside a try block. You can use more than one except block to catch exceptions, actually. So if you're looking for a particular type of exception, you can specify the type of exception you're looking for. So if you find a value error, if you're looking for a value error, you can specify that particularly, and then this clause will only occur, it'll only be activated if the try block produces a value error. You can also do, any type of error you can think of. You can do index errors. You can do 0 division errors. Anything you like, right? And if you want to catch all, so the equivalent of the if statement's else block is just except with no error name specified, which was the one that I was using before. So you can do things specifically according to specific error types, which is cool. That's good. You can even create your own. So, and this answers the question that we had posed at the beginning of the section. If you use the raise keyword, you can create any type of exception you like. Creates a value error. You can even raise exceptions with custom error messages. Exception. You're a fool. Exception. You're a fool. There you go. So, the raise keyword creates the exception. Things that are created using the raise keyword can be handled using try except blocks. They are errors in the proper sense. There's no difference between a value error that you raise and one that's raised by something that you use. In fact, the things that raise value errors in the functions that you use from the standard library or from wherever else are using raise value error in the same way that you are. So, so there you go. So that's raising errors. So in general, going back to this idea of what we would raise in the case where we wanted to return the maximum of a list that doesn't have a maximum, an empty list, you would probably raise a value error, because it is correct. It is correct to raise an error in that case because it does not have the same kind of baggage that returning false would. It is correct to say that you're trying to perform an action on something that is outside the domain of the expected inputs. So, generally speaking, that's when you would raise a value error. So let's talk about the different types of errors. Here are some common ones. Index errors. So, if you try to access something that's outside of the bounds of a list, you get an index error. I'm sure you've seen these before. If you try to perform an operation that doesn't work for a particular data type, you get a type error. So for example, if I have a list, 1, 2, 3, and I try to add 3, that is a type error. Can only concatenate list, not int to list. So you've probably seen that one before. The solution to that is you just put the 3 inside of a list itself, and there you go. Value error. When a function/operator is applied to an object of the right type but is otherwise inappropriate. So trying to take the logarithm of a negative number, or that would be a value error. Not implemented error. You guys probably have seen quite a few of these because Mark makes that the default thing to put into your code blocks when you need to answer the question. So the not implemented error basically just says this hasn't been implemented yet. I'm still working on it. Yeah. Generally speaking, when you're programming, you should probably implement anything that has a not implemented error associated with it. It's, for temporary use only, shall we say. Recursion error. You'll probably have seen some of these as well. If you hit the maximum recursion depth for a particular algorithm that you're working on, you'll get a recursion error. It tells you that you've recursed too much. Runtime errors. That's kind of your catch-all for errors that aren't classified elsewhere. I imagine if you managed to get Python to segfault, you probably end up with a runtime error. And zero division error. So computers cannot divide by 0. It causes an internal math problem that causes problems with the CPU. So, in regular, normal existence, you would say that infinity, 5 divided by 0 is infinity. But because computers are finite organisms, they cannot conceive of infinity. So when you do 5 divided by 0, you get a division by 0 error. So there you go. And finally, we have assert statements. And this is the last slide. So assert statements are not too complicated. They're syntactic sugar, basically, for the following. If A is equal to B, raise assertion error. Or, if not, some condition, raise assertion error. So, this is the same as saying assert A is equal to B. What an assertion error does is it says, if this is not true, raise an error. Otherwise, do nothing. So you'll probably, if you've been taking a look at the feedback that you've been getting for your assignments, you'll notice that assert statements are used pretty frequently within the within the test cells. The way that the test cells work in Jupyter Notebooks is if an exception occurs or if an error occurs while that test case is executing, then you don't get any marks for it. And if execution passes through without having any problems, then you get the marks for it. An assert statement will raise an error if you haven't met a particular condition, that condition being the test case we're testing for. So that's like the mechanism that sets up the error that is detected by Jupyter Notebooks and is then fed into the thing that keeps track of how many grades you have for each of the particular test cases. So there you go. That's testing and exceptions. If there are any questions about any of this, oh, it looks like my we are paying attention, fool. Yeah. Pity the fool that assumes attention is diverted. That would be fun, yes. Cool. So there we go. That's testing exceptions. I hope that's pretty clear. If there are any questions about any of that, please let me know, and we'll get through. We'll get all that done. I will answer your questions. And in the meantime, I will upload, download, reload, load topic 8, which is a much more rigorous academic exercise than topic 7, shall we say. Cool. All right. So. All right. If nobody has any problems with any of that, then we'll move on to classes. We are in class, and now we will discuss class. Huzzah. So. Hold on to your butts. This is going to get intense. So, classes. I think that it would be fair to characterize classes as the hardest remaining subject in the course. Being able to wrap your noodle around what classes are and what they're doing is not trivial. It's possible, but you have to engage a different part of your brain almost in order to really get what classes are and what they're doing. You need to start thinking less procedurally when it comes to programming. Up to this point, we've been dealing with programming in a purely imperative sense. That is to say, programs have been strictly a sequence of instructions. Now, essentially, we've been dealing with variables, and we've been dealing with functions. A class is a way of grouping together variables and functions. That's sort of your functional description of what a class is. So if you take a set of functions, group it together with a set of variables, smush them together into a single idea, and then create instances of that idea in the same way that you would create variables, you're kind of most of the way to the idea of what a class is. They are a little bit complicated, though. We're going to go through it. We're going to go through it carefully. And I hope that if any of you have any questions about any of it, you will please be active in the chat, because it is important that you understand this. What we are essentially talking about here is object-oriented programming. So you'll probably have heard the term object-oriented programming before. Object-oriented programming is, shall we say, the dominant paradigm at the moment. So you may remember we mentioned it at the beginning of all this, when we were talking about different types of programming languages. So Python is an object-oriented language. Everything in Python is an object. So if I ask for the type of L, that is, it's a list, class list. Class as in classes. Objects are concrete instances of classes, right? So L is a member of the class list. L is an object of the list class, right? L is a list. L is an object of the list class. That is the same thing. In Python, even something like the literal 8 is of class integer. Functions are of class function. Even something like value error is a class. So types are a class. All right? So everything is a class. Or everything refers to a class. Everything is an object. If it kind of physically exists, then it's an object of a class. Anyway. So we're gonna go through a few motivating examples before we get into like proper definitions and stuff. So we can raise exceptions in our code if it enters a situation that the code is not intended to handle. We just did this with exceptions. Find first even in the list. For x in list if x is not... So if there is no even number in the list, then it returns a value error as opposed to an index. Fine. We have many different types of exceptions that we can draw upon. Assertion error, index error, not implemented error, recursion error, runtime error, type error, value error, and bleh. I almost did it. I almost got the whole list without flubbing it. Zero division error. But what if none of these pre-existing exception types is appropriate for your particular scenario? Well, my good friend, it's good that you came today, because we are going to talk about customizing your exceptions. I already showed you guys exception. I pity the fool. Raise exception. I pity the fool. You can have a generalized exception type, and you can have a customized error that occurs inside of it. However, you can't try catch try except. In other languages, it's called try catch. You can't try except over this. No. And that's a useful thing to be able to do. So what we want to do is, rather than insert a customized error message into a generic exception object, what we want to do is create a new exception class. We want to create a new class of exceptions. So the way that you do this is reasonably straightforward. This is the simplest class that you will be expected to reproduce on a test or exam, because the exam is the next one. Get it? Topic 8 dot. Hi. There we go. Class. Fool error. Inherits from exception. Pass. Then I can raise a fool error directly. There we go. So class declares a new class. The next word is the name of the class. By convention, class names are capitalized, function names are not. That's why none of the functions have been capitalized so far, because capitalization on these identifiers is generally reserved for classes. That is a convention that is, I believe, pretty much language. That's not language specific to Python. That's general across many different programming languages. We then have a bracketed list of the classes that we inherit from. Don't worry too much about inheriting or inheritance. We're going to have quite a few slides on the idea of inheritance. For now, the idea of inheritance is that this class gets all of the stuff in this class. In this particular case, we don't actually want anything other than the stuff that's in exception. So we're just going to pass. We're not going to include any additional information inside of this class, aside from the fact that it inherits from exception. We are essentially relabeling the generic exception class as fool error, except we keep the well, relabeling is not a good term for it. It's not a relabeling because this guy still exists and is still usable. It's more like you're creating a copy with a new name. That's a much better way of thinking about it. And then we can raise, like, if we didn't have this, we wouldn't be able to raise just any old thing, you know? We wouldn't just be able to raise a fool error because it isn't defined. And, you know, we can't, you know, define it as a variable, because then its exceptions must derive from base exception. So this is deriving it from base exception. There we go. See if we have any questions. Slightly random question, but as I am demonstrating the object and type class, how do you go about creating a programming language? How do you go about creating a programming language? You write a compiler. Sort of in practical terms, the semantics that you write into the compiler as acceptable, those semantics comprise the language, right? Or, sorry, the syntax comprises the language. So a programming language is a combination of syntax and semantics, right? There are basically two approaches to this. One is to write a compiler, and then anything that the compiler compiles, that defines the language. The other way is to write a specification document. Generally speaking, specification documents are more common with the larger languages, like C, for instance. You know, I keep referring to C, the programming language. C has a standardization document, right? Where, you know, what an if statement looks like, what a while statement looks like, the way in which memory is handled, the way in which commands are compiled into object code, Those are object code is, roughly speaking, executable code. All of that stuff is put forward in a document, and then different vendors or companies will write a program which implements most of the standards document or all of the standards document. In the case of C, I think there are only 3 C compilers that implement the current up-to-date C standard, and Microsoft's C compiler is not one of them. But yeah, no, it's it's kind of like, from a practical standpoint, you have not written a programming language. So writing a programming language is in some sense the same as writing a program that reads in a document as a string, parses it into its component syntactic constructs, interprets the syntax in terms of a semantic, then produces object code or executable code based on that semantic interpretation, and then dumps out a executable file, right? A file that contains the instructions required to execute your program that can be executed. And once you've done all of that, you have written a programming language. When I put class error exception, can I explain again what exception in brackets does? Yeah, absolutely. So anything inside these brackets, you can think of it as this new class that we're defining is grabbing all of the stuff that's defined already in any classes that are specified here. So exception is already a defined class. It already contains definitions for this, that, and the other. By putting it in here, fool error is grabbing everything that is defined in exception and putting it into itself. The terminology, like, this is a very common operation inside of object-oriented programming languages. In C++, you would call this the derived class and this the base class. So exception is the base, and fool error is derived from it. So, yeah, it's so this class we're defining is a derivation of exception. Hopefully that helps. Anyway, let's break it there, and we'll be back in 10 minutes. Okay, class? We'll be back shortly. Hello and welcome back. I have returned for the third and final time, by which I mean second and final time today. Good. Excellent. Wonderful, wonderful, wonderful. So we can create custom errors. Long story short, we can create custom errors, and these errors can also be used by the except clause, so we can actually pattern match over them, which is useful. So let's move on to our second motivation for wanting to have something to do with classes. And that, my friends, is custom data types. So we have this family tree of characters from a well-known fantasy series, a popular series of fantasy novels by a British author. So essentially, let us consider what it would look like if we wanted to come up with some sort of formal way of representing these people and this structure inside of a computer's memory system, right? We might go about it something like, whoop, I hate it when I do that. Jeez. If I hit end instead of page down, it goes all the way to the end of the bloody presentation. So we might imagine doing it something like this, right? We have a series of dictionaries. These dictionaries have fields name, children, and spouse, and we fill out these fields based on, what a particular person's name, children, and spouse are, and we assign that to a dictionary. This is, and if we maintain that idea consistently for a number of people, we have created, in effect, what we would call a data policy. That is to say, we have a manner in which we expect these dictionaries to be constructed in order for them to be representing person data. So this is fine. This is actually not too bad. This can work. But it has some problems. So this data policy, one of the problems with doing a data policy like this, you guys remember, I think I've harped on this a few times in class now. If you have a data policy, or let's talk about functions for a moment. If you have a function that has conditions on its inputs, those should be documented, right? What you want to avoid at all costs, is implicit requirements, right? That's what makes your code unreadable to people, because people don't know what you're thinking, and you, 3 months from now, won't know what you were thinking. So the fewer things a person needs to know that aren't explicitly stated, the easier that code is for other people to use and your future self to use. So in functions, we generally talk about this with respect to conditions on the inputs, right? It's like, we want n to be greater than 0, or we want this to be a list and not a tuple, and stuff like that, right? It's slightly different with data policies. When, it's a related concept with data policies. The idea is, we have this expectation that anybody who is sort of a name, any person who is an entity within this family tree structure, which we are certainly not going to do out in its entirety, anybody who conforms, like, we expect people to conform to this particular pattern, this particular arrangement, this way of representing the data. However, we have to reconstruct it each time. Because we have to reconstruct it each time, we are probably going to make errors. So, for example, I'm just gonna grab this stuff right here. There we go. So we can say something like print, or well, anyway, we'll get into it. So if we have all of these guys, right, and we want to print, say, James P. dot name. Sure? Right? Oh, not dot name. I'm getting ahead of myself. If we want James P. at name, or if we want the name field of James P., that's how you would do it using a... Oh, I need to save it. There we go. That's how you would do it using a dictionary, right? Fine. Good. Excellent. What if you happened to misspell it? It doesn't exist. Key error name. So, because this is essentially repeated data entry, you have to expect that people are going to make mistakes because it's repeated data entry. If someone makes a mistake, then suddenly they don't have all of the things that a person object is expected to. So, you start running into bugs. Not a terribly difficult bug to find, but it's still a bug. The other thing that we're not taking full advantage of the tools that are available to us either. So there's no way of distinguishing using type or is instance. There's no way of distinguishing any of these records of people from dictionaries in general, right? Print type of Lily P. class dictionary. This does not tell us anything about the person, right? And if we call help on it, we get the help on dictionary objects, which is, kind of interesting if you've never seen it before, but not especially useful when it comes to the specific data policy that we're trying to enforce here. So, we have this idea that we may wish to create a customized data type. You can bundle. So, one way of thinking about this is rather than including all of this data inside of a dictionary, what we can do is we can create a class which bundles all of these data together. So we can create a custom data type to represent a person that automatically has spots for the properties you want. Spots for the properties you want, instantiates variables. Custom data types are called classes, in Python at least. In other languages, that's different, but in Python, a custom data type is a class. Every class is built from an existing data type. There's like one most general class, which you inherit by default if you leave it blank, but that's okay. We have to define a template for a custom data type. This is another way of thinking about classes. Classes are the templates for objects. So you write up a template, and then you fill it with data when you need it, right? It's like you have a rejection letter email template, right? And when you have to send somebody a rejection letter, you just fill in like name and position spots, and then it automatically sends out the, well, you know, you get what I'm saying. Templates. Templates are cool. Templates are fun. We can then create instances of the class. Each instance is called an object. When you use a class as a template to create a thing, that thing is known as an object. So let's try that out. Let's try this out. Let's create a class for people. Boop. Boop. Class, person, inherits from object. That's the most general thing that anything can inherit from. It's the same as leaving it blank. It's the default. You don't actually have to write it. Def underscore underscore init underscore underscore self. We're going to explain what all of this means. Self.name is equal to none. Self.children is equal to not empty list. Self.spoose. There's a spoose about the hoose. None. Now we can instantiate a person as an object of the person class. So the way we do that is we use the object, we use the class name, and then in here we put any initializing variables that we need to declare. In this case, there are none. Don't worry, we'll get there. So Harry is a person. Harry.name is equal to Harry Porter. Print Harry.children. Let's see what this does. So, and just for fun, print Harry.name. Harry Porter. So, so what we have essentially done here is we have elevated what were previously keys of a dictionary to the status of variables within a class. We sometimes also call these attributes. Attributes of a class. So, yeah, these are attributes of a class. The way that you access the attributes of a class is the same, or the attributes of an object is the same way that you access the methods of an object. So you guys probably recall at this point, you can do, you know, the rain in, or let me do this in terminal. If you do the rain in Spain falls mainly on the poor dot split on space, that splits your string up into a list of strings along the space character, which is, you know, a fast way of chunking a sentence up into words, right? You probably have seen this a few times on the assignments and I think on the tests as well so far. So, dot split. The way that split is being called here, it's not split this, that, right? Name split is not defined, right? That's it. This is a method. This is a method of the string class, right? This is an object of type string. The split method applies to string objects. That means that you can't split just anything. It has to be string, right? So split is not a function in the function. It's not a function in the global namespace. It's a method within the namespace of string. One way that you can get around this, I think this will work, str.split. Yeah. So you can actually access the method by making reference to the class name itself, right? Same idea, but this is a method, right? The way that you access the attributes of a class is the same way that you access a method of a class, and that is using what's called dot syntax. So Harry.children, Harry.name. It's like, you'll get used to this pretty quickly, but it's like object field, object field. Where the field is another object, you can continue this. So it's like, planet.country.city.street, You can continue to chain together these dot syntaxes, dot cleanup, virtually infinitely. So, yeah, let me see if there are any, no questions so far. Okay, so dot syntax is how you access the things that are inside of a class. You have to make reference to the object, though. So if we take, I'm getting ahead of the slides a little bit, but if we okay. First, I'll show you how to write a method, right? So this init thing here, that is a method. It's a method that we're using to define the attributes of the class, but we can just write general methods in by defining them like functions inside of the class, inside the body of the class. So def make old, which is a fun one to do to humans. So has to take self. I'll explain why in a bit. Self.name is equal to old plus, or concatenate self.name. So if I make a call to Harry.makeOld somewhere between assigning the name and then printing it, there we go. I have to save that. I keep forgetting to save it. It says old Harry Porter. So so we assign the attribute. This line is irrelevant. We call this method. Execution jumps into here. Self.name is assigned old concatenated with self.name. So that modifies the internal state of the attribute of the class, or attribute of the object. And then when we print it, we can see that change. Cool. So that's a fairly conventional use of the method, right? Cool. So let me explain some stuff. The self here, and this is a tricky one that most people, like a lot of people, tend to have difficulty with this idea. The first argument of any method, all methods actually, is a self-referential. It's a reference to the object on which the method has been called. So when I say Harry.makeOld, what's essentially happening is that Harry is designated as self. Now, this is kind of a little bit bass-ackwards, because you're like, well, self is an argument. It's not being used as an argument here. It's happening with dot syntax. What's going on here, Mr. Professor, sir? And it's like, yes, because that's the default. That's kind of syntactic sugar that Python has thrown in there to make everything work correctly. Another, like an alternative way of doing that is you would say make old Harry. But the problem with this construction is that make old isn't a function. It's not a function. It's a method within the person namespace, right? So person, like you have to know that make old belongs to person. So if you're going to use it that way, you have to put person dot make old Harry. These two are equivalent constructions. So if you run this, you'll see we have now old Harry Potter. So he's now doubly old. So yes. So in general, Harry is self. All right? If you do it this way, if you make reference to the object directly, anything that comes before the dot is mapped to the first argument here. Flat out. That's it. That's everything. So yeah, so that's how self works. Let me see if there are any questions. If there are any questions about that, let me know, because that's an important point. Yeah, so let me get into init a little bit, now that we know what self means. It operates a little bit differently in the case of init, but essentially it's the same thing. So just replace the dot with an equal sign, basically, when it's the initialization. So Harry is equal to person. We've got self.name, self.children, self.spouse. The underscores here indicate that init is a magic method. It's a method that's already bound to particular things. We're going to see a few of these later on. There's actually a large number of them. If you remember when we took a look at help dictionary. So help dict. You can see there's a lot of these methods that have double equal signs or double underscores. Yeah, there you go. Init. Ta-da! There's a lot of these guys that have these double underscores attached, and what it means is it's essentially mapped to some kind of system function. So not equals, for example, or NE is not equals, and that is basically, it defines the behavior of the exclamation mark equals operator. In the same way, GE defines greater than or equal to. Right? LEN defines what length means for this particular data structure. So there's a whole bunch of them. Right now, only worry about init. So one of the things that you can do with init is you can provide it more arguments. So let's say we didn't want it to be possible to create a person object without that person having a name. We can insert that as an argument of the initialization function method, and then we can use that variable inside of this block of code to give a default value to the attributes. So now, if we run this code, we should get a problem once I save it. Yes. Init missing one required positional argument n. So when we initialize Harry Potter as a person, instead of explicitly assigning to the attribute, we provide the initial value to the initialization function itself, and then it just works. right? So you actually have control over the number of arguments that you're putting here, in the same way that you have control over the number of arguments that you put into a regular function. It's just the first one always has to be self and always has to be present. Let's see. Keep getting a name error. Name. Are you using an apostrophe there? Because you should be using a period, not an apostrophe. And it should be Harry.name, not name.Harry. Right? That might be the other problem. You don't do name.Harry. You start with the object, and then you go to the attribute. Always. Okay? Cool. So, I wonder exactly how many slides I've jumped ahead of. Probably quite a few. But anyway. So, let's just go through these then. So to define a new class, we use the following syntax, right? We say that my class name extends what it's built on. So person extends object, right? At the beginning, my error extends exception. Base class and derived class is another way that you'll probably hear this referred to. This is the base class. This is the derived class. We can always extend the built-in starting point object. And object is so basic that if you do not include any class name here, it assumes you just meant object. Now we have to define a template for our customized data type. So we need to decide. So there are a couple of fun things that you can do with this, right? So we're defining not only how our data is initialized, but also how it can be used. So we are defining operations that we can perform with this data. One of the other magic methods that you can introduce is def add. This overwrites the function of the plus sign operator to whatever you make it. So I'm going to do something fancy here. I'm going to say self and other dot spruce is equal to other dot name, and other dot spouse is equal to self dot name. So what this function essentially does is it's now become a marriage operator. We can add two people together and marry them. So if we define two people, let me just blow some of that out. Let's say we have Harry Porter and Nancy equal person Nancy Drew of Nancy Drew Mysteries fame. We then, if we say Harry plus Nancy, then print Harry dot spouse and print Nancy dot spouse, you can see Harry dot spouse, or I guess we can make it a little better. Harry is married to, and Nancy is married to. Syntax error. Don't marry syntax errors. So Harry is married to Nancy Drew, and Nancy is married to Harry Porter. And I I know I'm intentionally misspelling it. So yeah, there you go. So this is not only so a class is not only a method of containing data, although even a class that just contains data is still a useful thing, but classes can do so much more than that. Any way in which the data can be usefully used or interpreted or modified, those actions can be made methods of the class. So, you know, relative to family trees, marriage is a fairly common operation. So it would make sense to have an operator for it. So, yeah, anyway. See if we have any questions. Nope. Good. Init, 2 underscores on each side, is a special function called an initializer. It is called whenever we make a new instance of the class. Yes. Yeah. In other languages, we would call it a constructor. Inside the initializer, we can define instance variables that are associated with each instance of the class. Instance variables are sometimes called members or properties or attributes. Calling it members is very C++. Member functions, member variables. But properties and attributes is more Python speak. Different instances of the same class will have independent instance variables. So notice in our example here, we have defined 2 different persons. We have defined Harry and Nancy. Although they have both made reference to the same initialization function, these are separate class instances. These are different objects. Their information does not interact with itself. Like, Harry.name is not modified when Nancy.name is modified at all, ever, for any reason. And this example should show you that. So they are separate and distinct. In the same way that declaring 2 lists, they don't interact unless you've done something to make them interact. In that way, 2 objects do not interact unless you tell them to. So, we can also add functions to a class. These are called methods or member functions. I'm probably going to refer to them primarily as methods. So in this case, we just have a test for marriage test. Self.spouse is not equal to none. That is that is whether or not, that is the state we define as being marriaged. So, there we go. Are there any questions about any of that? I will take a moment to answer any questions that you might have before we move on to our next component of today's discussion. Oh, I have a question, actually. Is Harry self or the class person? So, Harry, in this example, is an object... there we go. Harry is an object of the class person. An object of the class person. Harry is self for all operations that are called on him. So, in this case, Harry would be self here. Nancy would probably be other. If I call Harry.makeOld, Harry is self. Yeah. So the way that you treat self here is as an object of this class. So you can actually call any of the methods that are defined for person with reference to self. This is why This is why we're using the same dot syntax to access attributes inside of the class as we're using outside of the class, except the difference being, instead of doing Harry.name, we're doing self.name, because it's general, it applies to all objects of that class. All objects. Cool. Can I go over init one more time? Yes. Yes, I can. So, init is the initializer or the constructor. It is called automatically upon the creation of an object of this class. Right? So, whenever we create a new person, init is automatically invoked. It's automatically called. Which means, in this particular case, it's going to look for any of the attributes that it's requiring in its or any of the parameters that it's requiring up here. It's going to look for them. So if it doesn't find a name, it'll complain, and any code that's inside of here will be executed, and any variables within the self namespace with it that it uses will be declared, right? All of the code that's here gets run only once when the class is initialized. So if you wanted to, like, you know, print something like person successfully created self.name, something like that, you can see that code is just general. That's just down for general execution. Right? You can put anything you want in there, but generally speaking, initialization functions tend to be pretty sparse. They tend to be reserved primarily for the initialization of variables. So yeah, self, Harry, n parameter, person, here, creates an object, and then you can operate on the object. Cool. All right. So, let's continue on. Let's keep blasting through. So in Python, everything is an object. I talked about this at the beginning of the lecture. Every object is an instance of a class. So even stuff like type of plus is not a... Oh, maybe that doesn't work. Interesting. It is still a thing, though. Plus is a function. But, yeah, so if we were to call type over our person object, what we would get is class main.person. So that this is to say that the person class has been defined within the main namespace or workspace. So basically everything that's inside of here is occurring inside of underscore underscore main underscore underscore. Anything that you're bringing in from the libraries, that's all defined elsewhere. So, the class definition defines attributes, properties, variables, members, and methods that are common among all instances of the class. So it doesn't matter, you know, it doesn't matter who you are, you have a name, if that makes sense. Attributes of a class or an object are referenced using dot notation, as we've already stated. Here's another example, a somewhat more geometric example. So, let's define a class for points in Euclidean space, two-dimensional Euclidean space. Class point inherits nothing. Define initialization. We shall take self x0 and y0, x0, y0. Self.x is equal to x0. Self.y is equal to y0. why not indeed? We then want to define a few methods for this. I believe it's self.scale takes self and some value k and just multiplies self x and y by k, so it's just scaling it relative to the origin. Self.x is equal to self.x times. Actually, you can just do times equals. Save some space. Self.y and some brain cells times equals k. Def magnitude self. So return. So the magnitude of so the distance between 2 points in Euclidean space is, of course, Pythagorean theorem occurring over the difference of their coordinates. So self and other return self.x minus other.x squared plus self.y minus other.y squared. All that to the power of 0.5, which is our fancy, handy way of doing the square root. So there we go. And I think there's like translate. Yeah. And we want to be able to move. So def move self dx dy self.x plus equals dx self.y plus equals dy. There we go. So there you go. We've got x and y coordinates defined. We've got some functions. We've got some methods. Cool. Methods are, of course, called using dot notation. The first parameter, named self by convention, is bound to the object. So p.move11 is the same thing as point.move p11. Right? This is the way that exactly matches the manner in which the parameters of the method have been written into the class, but this is slightly more convenient to write. So this is what you're going to see most of the time. The init method is implicitly called when an object is created. Its parameters have to be supplied at object creation. So, like so. So if we wanted to create a point, P is a point, we have to provide an x naught. We have to provide an x naught and a y naught. So let's say 5 and 8. Q is a point 1 and -4. Let me just comment that out. There we go. We're not actually printing anything yet, though. So if we print, for example, p.magnitude, distance is better, actually. Distance, more accurate description. P.distance q, we get 12.64, etc., etc. Cool. Which I think if you actually calculate that, you'll find that's pretty accurate. So, this is all well and good. But what if we want to print an object? You know, it's possible that we may wish to print an object to see what it's doing. Print Harry. What do we get? What do we get if we try to print Harry? We get main.personObject at this thing, which is actually a memory address. So the thing that it's doing is it's giving you the memory address of the object, like where it is in your system's memory. This may or may not be useful, because, you know, you can actually, in the same way that you can make aliases with lists, you can make aliases with objects as well. So you see I've assigned Harry2 to Harry1, and if I print both of them, you'll notice they have both the same memory address, which of course means any modification made to Harry1 will be viewable in Harry2. Like, they're both referring to the same memory. But what if I want to display something more useful? Well, what we do is we override the string conversion method. We can say return a person named string convert. Actually, we wouldn't even need to. String.name. Then, self.name. There we go. A person named Harry Porter. So this little guy here, overrides the showing of the memory address in favor of literally anything that you may wish to specify. This can be much, much more useful than just getting the address of the object. If you look ahead in the assignments a little bit, there's a assignment question where you're programming checkers, the board game checkers, and we're in that class. You use the string conversion method is used to display a checkers board, rather than, you know, any nominal, like just simply the state of any particular attribute. So yeah, exactly. By default, print outputs an internal representation, usually memory address of an object. This can be overridden by providing the string method. And I think that's a good place to leave it for today. If there are any questions, I would love to see them in the chat. Otherwise, I'll let you get to your tutorials. Sorry. I tried to protect headphone users on that one. Yes. All right. Can we go over string one more time? Yes. So, in the same way that init overrides the initialization or the construction of the object, and in the same way that add overrides the definition of what plus does, what string, str, that overrides the behavior of string conversion. So it's interesting, because you can actually get the same thing if you perform like string conversion explicitly. So, you know, if I convert it to a string, then multiply it by 3, that'll repeat it 3 times, right? It's a string now. What this does is it overrides the string conversion function, right? So the reason that this works with print is because when you print something, one of the steps in that procedure is that it calls string conversion to convert whatever it is you want to print to a string before it prints it, because it has to print a string. So, you know, if you're printing the number 9, it's going to convert that to a string before it prints it, because you don't want 9 the ordinal value of some character. You want 9 the integer, typically speaking. So when you override string, you then, anything that you return from that function is going to be returned as the result of the string conversion. So when you print the object, the print function invokes string conversion on the object, and then that causes this method to be executed, and the return result of this method becomes the return result of the string conversion function, which is what the print statement prints. Hopefully that's reasonably straightforward. Cool? We cool? Is that good? Okay. Give it a moment. Awesome. All right. Well, that seems like that's everything, so I'm going to let you get to your tutorials. Thank you very much, everybody, for tuning in today. We'll see you again tomorrow. Etc., etc., tomorrow. And hopefully we'll finish off classes. Not class in general, class is the topic. Sorry, we still do have a few weeks. Take her easy, folks.